With that, I'm excited to introduce the author of CVXPY Gen. I don't think you're talking about that, actually. I think you're talking about something completely different, right? Yeah, it's talking about something completely different. So I present to you Max.
Right. Thanks, Bart, for the introduction. I'm Max. I'm one of Stephen Boyd's PhD candidates. And today I'm talking about learning parametric convex functions, LPCFs in short, which is meant to be like a simple, useful tool for kind of bridging data-driven modeling and system identification with, the nice properties of convex optimization that we all appreciate. So parameterized convex function is basically a function that takes two inputs. One is a variable that we call a variable. The other is a parameter, and it can have the outputs. And we want that the function is convex in X for every parameter value theta. That's sort of what we need to know, and that what appears in DPP, for example, which we've heard a bunch of times. I think I don't have to talk too much about DCP. We talked about it quite a bit, so I think I will skip this slide. The idea of this framework is to create like a simple neural network architecture that follows the DCP rules, and sort of takes as input. We can see on the top left the variable X and the parameter theta, and then the expression Y that comes out of it is basically a DCP expression. And the idea is basically to then be able to learn sort of all these weights, V, W, omega. And when we finish with learning, we sort of have a DCP expression that we can then use, say, in a CVXPY problem. And this subnetwork side on here, you can basically think of it as a reparameterization of theta that maps theta into these matrices V, W, and the offset vectors omega, which then sort of characterizes little neural network. And yeah, so we could zoom into Psi. It's not too important. It's just like a similar architecture where the output is sort of the flattened vector of all the weights and biases of sort of the main neural network. So how do we restrict this network? We basically want the output to be in DCP, and for that we make like a couple of very simple assumptions. So we say that the activations phi, they need to be convex and non-decreasing. They are kind of the atoms in our DCP tree. And then the weights should be non-negative to have sort of the non-decreasing properties of the expression. And then it turns out that the resulting thing is actually a DCP parametric convex. And then we take data and fit that PCF to that data. So we have, again, as in every machine learning setting, we have a data set with pairs of inputs and outputs. Input consists of variable and parameter. We kind of define that boundary there in the input vector. And we take a generic loss function and regularize, and we minimize an average loss of the data plus a weighted regularizer. And the package gives a couple of different options for these functions. So we created this open source package. You can pip install it through, you can pip install it from the Python package index. It's quite customizable, so you can tune your number of layers and the width of your layers. Choose a couple of different activation functions, and then you can basically export either a CVXPY expression or a JAX expression that you can then further use downstream in your optimization application. So here's like a little hello world example. We will expect that you have your data ready. It might be observations or simulations. It's just a rate. We have n rows for the number of data points, the outputs, and variables, and the parameters. You instantiate a PCF object, you fit it. There's, of course, a couple of settings that you can play around with. And then you define a CVXPY variable x, CVXPY variable theta. Then you call the toCVXPY method on that PCF object. You pass in these two CVXPY objects. And that gives you a CVXPY expression y, which basically follows your DCP. And then you can use it on a CVXPY plot. The way this works is, you remember we had this psi network that sort of map data to the neural network weights. Whenever you assign a value to theta, then we make use of a CVXPY callback parameter internally, and then the v's, w's, and omegas get updated. Then when you say prop.solve, or you evaluate any CVXPY expression that involves the PCF, then sort of the psi network is not relevant anymore. Then you're dealing with sort of the main little network. We have a couple of extensions. For example, we can add a quadratic term to the output. In fact, we can add a low-rank plus diagonal term also. That is useful in many applications. Can require monotonicity, which is enforced by just positivity of the V matrices, and a couple of other extensions that might be useful. So I'll give two quick examples. This one is more of a example where the piecewise affine function, where the variable is sort of input x, and then we have the slopes, the sort of piece points of the parameters. It might be a PCF itself, it might be convex, but it can also be like a non-convex piecewise affine function. And then we sample a bunch of data points and fit PCF width. And then we see that we basically recover the true function when it is a PCF as expected. If it's not, we're basically rediscovering the least squares fit, which is kind of trivial, but it's just like a little example. This one is a bit more realistic. This is a function that models battery degradation, where sort of as the variables, the fastest changing quantity, we have the state of charge and the charge rate. And this whole thing is parameterized by sort of the lifetime accumulated throughput A, the battery capacity Q, and the temperature that we're operating at T. And the remaining symbols are like physical constant or like battery specific constants. And again, we sampled a couple of typical values with the PCF. And here's the result. We can we recover the true function through like some reasonable error. This is it already. So this is meant to be like a simple tool that helps bridge system identification and convex optimization. You can install it